I welcome you all for today's free KCET online class 2021. Myself, Shreenivasa M Bhat, lecturer in physics, Government PU College, Carnot. Today, I am going to teach first PUC physics topics, thermodynamics and kinetic theory of gases. I'll go to the questions directly. The first question. Is like this. An ideal gas undergoes 4 different processes from the same initial state as shown in the figure given below. The 4 processes are adiabatic, isothermal, isobaric, isochoric. Out of 1, 2, 3, 4, which one is adiabatic? So you can see in the figure there are 4 lines named 1, 2, 3, 4. So which one is adiabatic? Simple. So line 1, O21 is there, no? Line 1. So that is having constant volume. So I can call it as isochoric. Isochoric. Then number 4, constant pressure. So isobaric. Isobaric. Whereas number 3 and 4. So this is a gradual fall in pressure. Whereas in the second one, the number line 2 is a sharp fall in the pressure. So that indicates the adiabatic process. Okay, adiabatic, where there is a sharp fall in the, you have seen in the Carnot cycle. Whereas adiabatic expansion is much steeper than the isothermal expansion. So this is isothermal. Okay, so the answer is isothermal is represented by the line 2. So the option B is the right choice. Then the next question. Consider 2 containers A and B containing identical gases at the same pressure, volume and temperature. The gas in container A is compressed to half of its original volume isothermally, while the gas in the container B is compressed to half of its original volume adiabatically. The ratio of the final pressure of gas in B to that of gas in A is. So here in this question, there are 2 containers A and B. So in A, gas is compressed isothermally, whereas in B, gas is compressed adiabatically. So in A, gas is compressed isothermally, so volume becomes V by 2. So pressure P, volume V becomes pressure PA, okay, volume V by 2. So therefore, what is PA? So P into V equal to PA into V by 2. So this is the equation. P1 V1 equal to P2 V2, we can say, in case of isothermal process. So therefore, PA equal to final pressure in gas A is equal to, it is 2P. Now in B, container B, the gas is compressed adiabatically. So P1 V1 for adiabatic change, P1 V1 power gamma equal to P2 V2 power gamma. This is the formula which connects the pressure volume initial and pressure volume finally. Okay. So here initial pressure volume same, P1 is P, volume is V, power gamma equal to P2. P2 I take say PB in the container B. Okay, so PB into volume finally V by 2 power gamma. Okay, power gamma. So now this simplifying this PB I want final pressure. So V power gamma here, V power gamma cancels. So 2 power gamma here it comes. So 2 power gamma into P. Finally we need the ratio. What is the ratio? Ratio of final pressure B to that of A. So PB divided by PA. PB divided by PA. That is 2 power gamma P upon 2P. So that is equal to 2 power gamma minus 1. So the answer is option number A. Option A is the right answer for this question. Now I move to the next question. That is question number 3. An ideal gas undergoes isothermal process from initial state I to the final state F. Choose the correct alternative which satisfies isothermal process. So isothermal process means temperature remains constant. So when temperature remains constant, we know that the internal energy of the gas remains constant. Internal energy is the decided by the temperature. So internal energy remains constant. Okay, equal to constant. Internal energy U is constant. It will not change, neither increase nor decrease. So therefore, change in internal energy, say I can write du. du equal to 0. There is no change in the internal energy whenever there is a isothermal process or when temperature is constant. Then apply the du value equal to 0. Substitute in first law of thermodynamics. First law of thermodynamics states that amount of heat supplied to the substance dq equal to change in internal energy plus amount of work done by the gas. This dw stands for work done by the gas. There is something opposite in chemistry I heard. So here amount of heat supplied to the gas dq, du change in internal energy, dw work done by the gas. Okay, so du 0 means it becomes dq equal to dw, as the option D is the right choice. du is 0, dq is dw. So then I go to the next question, number 4. Figure shows PV diagram of an ideal gas undergoing change in the state from A to B. Okay, 4 different parts, 1, 2, 3, 4, as shown in the figure, may lead to same change in the state. Okay, may lead to same change in the state. Okay, statements are A, change in internal energy is same in 3 and 4, third and fourth cases, but not in first and second. The change in internal energy is same in all 4 cases. C is work done is maximum in case 1. D is work done is minimum in case 2. So in this question here, you should know some facts. That is the 4 cases are there here. We can see clearly. Case 1 here, this one, it is the topmost part. Okay, 1 it is. And I draw some vertical lines from A and B to the volume axis. Okay, so here, how do you get work done and how do you get internal energy from the graph? So here from A to B, 4 different ways gas undergo transformation changes. So internal energy change is same because the initial and final states are same, temperatures are same. So change in internal energy will be same in all 4 cases. So hence B is the correct statement. Then work done to calculate the work done in 4 different cases. If I drop the perpendicular from A and B to the volume axis, the area under the curve, okay, area under the curve is maximum for the curve number 1. Maximum area below this curve with respect to x-axis, that is volume axis. Hence work done is maximum in case 1. So the option C, statement C also correct. Work done minimum in case 2 is wrong because work done is minimum in case number 3. Here is the work done minimum because minimum area between volume axis and the curve. So therefore BC correct means option B is the correct answer for this question. Then I move to the next question, number 5. Consider PV diagram for an ideal gas shown in the figure. Out of the following diagrams, which represent TP diagram corresponding to the above PV diagram? So here is one PV diagram given, corresponding to that TP diagram is required. So let us see the diagram here. Pressure and volume is given here one condition. Even we can understand seeing the curve, it is a isothermal process. P inversely proportional to volume. This is what shown in the graph here. P inversely proportional to volume. So it is isothermal process. This is a isothermal process. If it is isothermal process, temperature is constant. Temperature constant means what it says, temperature constant. Which graph is temperature constant? Yes, A is constant, D is constant. B and C not constant. T value increasing, here also increasing. Now if it is constant, which one is correct among A and D? It is C. Initially at point 1 pressure is more pressure. At point 2 pressure is less. So point 2 less pressure, point 1 not possible here. Okay, here it is possible 2 at point 2 less pressure, at point 1 more pressure. Okay, more P here less P. Okay, so therefore the option D is the correct choice for the question number 5. Then question number 6, a real gas behaves more closely to an ideal gas at high pressure, low temperature, low pressure, low temperature, high pressure, high temperature, low pressure, high temperature. 4 combinations are given. So real gas is closely to ideal gas at low pressure and high temperature. This is because only at low pressure and high temperature, the force can be neglected between the molecules. Interactive forces can be neglected. Otherwise, there will be interaction between the molecules when it is high temperature. When temperature is high, interaction between the molecules can be neglected. Force is negligible. And low pressure means the gas molecules will be very less in number in a way. So therefore, the behavior becomes ideal or very close to ideal, so that volume of the gas molecule is negligible compared to the entire volume of the gas. So that are the required criteria for ideal gas. So that is obeyed when it is low pressure and high temperature. High temperature means, another way you can think, high velocity will be there for the gas molecules. Then option D is correct. Then I go to the question number 7. An ideal gas undergoes cyclic process ABCDA as shown in the PV diagram. The total amount of work done by the gas. Okay, so in case of PV diagram, the work done is nothing but the dimensional formula of PV is equal to energy, or same as work. So amount of work done is the area under this curve, area within this loop. So work done equal to so much. Work done equal to area within the loop. So that is equal to, so work done here, work done is equal to area under PV diagram within the closed loop. So write work done equal to area under this. So change in volume, that is say AB, length AB, that is 3V0 minus V0, 3V0 minus V0 into change in pressure. As it is a rectangle, 3V0 minus V0 into 2P0 minus P0. So now this is equal to 2P0, 2V0 into P0. That is equal to 2V0 P0. Okay, so this is the answer. But here you see the cycle, it is cyclic process. From A it starts, B, C, D, A. The work done during expansion from A to B is comparatively lesser than when gas is compressed from C to D. C to D it is compressed at pressure 2P0. So work done is more on the gas than work done by the gas. And it is, we can say it is anti-clockwise direction. So work done, it can take negative. So work done is minus 2P0 V0, as it is anti-cyclic or anti-clockwise direction. So the answer is option D is the right answer. The next question is number 8. For gas undergoing adiabatic process, it is found that PV power 0.4 equal to constant. Then the gas must be monoatomic, diatomic, triatomic, polyatomic. See, comparing this with the standard equation connecting the temperature and volume in case of adiabatic process, PV power gamma minus 1 equal to constant. Okay, so then it is gamma minus 1 equal to 0.4. We can say gamma equal to 1.4 or 7/5, which is nothing but diatomic gas. And another relation in terms of pressure also you may require sometimes. So 1 minus gamma, P power 1 minus gamma into T power gamma is constant. That means here we can write T1 V1 power gamma minus 1 equal to T2 V2 power gamma minus 1. Sometimes we may use. Or here also P1 power 1 minus gamma into T1 power gamma equal to P2 power 1 minus gamma into T2 power gamma. So like that we may have to use in some problems when pressure and temperature relations are given in the question. So the option B is right here. It is diatomic gas based on the ratio of specific heats. This gamma means ratio of specific heats. It is Cp by Cv. Okay, ratio of specific heats. Gamma value 4/3 for monatomic gas, 7/5 for diatomic or 1.4, and 1.33 or 4/3 for triatomic gas. Then I go to the next question, number 9. 3 copper blocks of masses M1, M2, M3 kg respectively are brought into thermal contact till they reach equilibrium. Before contact, they were at T1, T2, T3 with the T1 greater than T2 greater than T3. Assuming there is no loss of heat loss to the surroundings, the equilibrium temperature is. So there are 3 blocks. When they brought in contact, their temperatures become finally this is the mass M1, another mass M2, different masses. Okay, so their final temperature after equilibrium attained is T. So now, so hot body loses the energy, heat energy, whereas the cold body gains the heat energy. So we can take, so we know already the loss, heat loss, delta Q, in terms of mass into specific heat into change in temperature is ms delta T. This is the amount of heat energy gained or lost whenever temperature of the body changes. Mass into specific heat into change in temperature. If you write for body M1, mass M1, so it is mass M1 into specific heat, same for all copper blocks, into change in temperature, heat lost by that hot body. So T1 is obviously more than the final temperature T. Then next heat for second body M2, we don't know whether it is lost or gained. It is intermediate temperature. So I take here along with this, it also lost. So M2 yes and T2 minus T, and that is equal to heat gained by the cold body, say mass M3 yes and T3 minus T. Now SS cancels through. So here the heat gained for this we can write T is greater. T is greater than 3 obviously, because the equilibrium temperature must be in between T1 and T3. So T1 must be greater than T, whereas T3 should be smaller than T. Okay, so T should be in between them. So now S cancels through. So what happens is M1 T1, okay, plus M2 T2, I write. Okay, then from RHS M3 T3, this one T3 is less, T is more. So we have to write T minus T3. So I bring to the LHS, so it becomes M3 T3. Whereas M1 T minus T is there here. So I take into RHS. So M1 T plus M1 T plus M2 T plus M3 T. Now taking a common T out from the RHS. So it is M1 plus M2 plus M3 times T. LHS is same. So the option B will be the correct choice. So option B will be the correct choice. M1 T1 plus M2 T2 plus M3 that is the LHS. When I divide throughout by M1 plus M2 plus M3 to the LHS, I get T equal to option number B is the right choice for this question. Then I go to the next question, number 10. A certain triatomic gas under pressure P occupying volume V allowed to expand isothermally to a volume 8V. The gas is compressed adiabatically to a volume V. The final pressure of the gas is. So firstly, initial pressure and volume becomes isothermally, it is compressed. So it is expanded isothermally. Isothermal expansion. So pressure we don't know. So volume is, say, initial volume, it is V, initial pressure is P. So P into V product, P1 V1 equal to P2 V2. So here finally, what happens to the pressure? So volume is 8V, so pressure must be P by 8. Isothermally means pressure, because initial product PV, final product also should be PV only. Then, so final pressure here in the isothermal process, P by 8, volume is 8V. Now this is changed, P by 8 into 8V power gamma it is. Why it is? Adiabatically we are changing, no? Adiabatically. Adiabatically means the initial pressure P by 8, volume 8V, you have to take gamma, that is equal to final pressure we have to find out, say P dash. Okay, volume is finally V only, so V power gamma is required for adiabatic process. Now you have to simplify this equation to get P dash value. So here simple, P by 8 power gamma is there. Okay, V power gamma here and RHS V power gamma cancels. So P dash equal to P into 8 power gamma minus 1. Okay, so that for P dash equal to P into 8 is, gamma is how much for triatomic gas? Gamma is set, it is 4 by 3 for triatomic gas. Gamma is 4 by 3. 4 by 3 minus 1. Okay, 4 by 3 minus 1. It is 1 by 3. P into 8 power 1 by 3. 8 power 1 by 3 means it is a cube root of 8, that is 2. So 2P is the answer, that is option number B is the correct answer. For question 10, option B is the right answer. Now question 11. The pressure, temperature at the top of mountain are found to be 90 kilopascal and 6 degrees Celsius respectively. The corresponding values at the bottom are 100 kilopascal and 27 degrees Celsius. The ratio of the densities of air at the bottom to that at the top of the mountain is. So ratio of densities of air we have to get at bottom and at the top. Now pressure is given here. This is the, I will take P1 at the top of the mountain. I'll take P1 and temperature is say T1. 6 degrees Celsius is given. In thermodynamics you have to use in Kelvin only. So it is you are substituting in the ideal gas equation or anywhere you have to substitute the temperature in Kelvin. So 6 degrees Celsius is 279, add 273, it is 279 Kelvin. Now the final pressure is 100 kilopascal. Okay, final pressure P2 is 100 kilopascal and final temperature T2 is 27. You can write 27 as 27 plus 273 as 300 Kelvin. So now what you have to do, get density ratio you have to get. So density at the bottom, it comes at bottom here. So it is ρ2 and here at the top means ρ1. So to get the ratio, ρ2 by ρ1. Okay, ρ2 by ρ1 is required. ρ2 upon ρ1 is the required data. Okay. Now, firstly, the pressure is related to this temperature, density, all this by the relation rho into RT upon M. Okay, M or M naught, where M naught is the molecular mass. So P is pressure. It is just similar to the ideal gas equation, PV equal to RT. Okay, so PV, volume is mass by density. So we can take like that. So this implies P, pressure depends, R is constant, M naught is same for the air at the top and bottom. So here pressure is directly proportional to rho into T. Now what I get? I take P1 by P2 equal to ρ1 by ρ2 into T1 by T2. Which implies what I need to get is a ρ2 by ρ1. ρ2 at the bottom. I've taken P1 at the top, P1 at the top mountain, and bottom I've taken 100 kilopascal, that is P2, and so ρ2 by ρ1 you have to get. If you get reverse also, there is the answer. So ρ2 by ρ1 equal to P2 by P1, P2 by P1 into T2, T1 by T2. Okay. Now substitution will give you the answer, that is P2 by P1, P2 pressure at the bottom is 100 kilopascal, 100 kilopascal divided by P1. P1 is 90 kilopascal. Kilopascal cancels. Whenever it comes a ratio, no need to write 10 power 3 always. Okay, so it can be cancelled here. T1 by T2, initial temperature, or say temperature at the top, first case 279 upon temperature at the bottom is 300. Okay, so that is equal to, now we can see here zeros, you can cancel with the zeros. Okay, so 3 ones, 3 can cancel here with the 279, it is 93. So the ratio is 93 upon 90, or 93 upon 90 is nothing but 31 by 30. 31 upon 30. So the option is D is the right choice. Okay, so that's all about this question 11. Question number 12. A cylinder containing an ideal gas in vertical position and has a piston of mass m that is able to move up or down without friction as shown in the figure. If the temperature is increased, then what happens? Both pressure and volume of the gas will change. Only pressure will change according to Charles' law. Option C is volume will change but not pressure. Pressure will change but not volume. So here temperature increased in this situation, they said. So by increase in temperature, what happens? So here there is a mass m. So who is exerting pressure on the gas here? That is weight of that object placed, that is mass placed. So pressure exerted on the gas equal to force by area. Okay, here force acted upon by this mass is nothing but its weight, mg by area. So therefore here you can see mga. These three values do not change here. So they are almost remaining same. G value also same at a given place. So pressure is constant. So this says that pressure is constant. When pressure is constant, so it is given ideal gas. What do you say for ideal gas if pressure is constant? PV equal to mu RT or nRT, we can take ideal gas equation where P is constant, R is constant, mu is constant, V is directly proportional to temperature. This is nothing but Charles' law. Okay, so pressure remains constant, but volume increases. They said temperature increases, no? Temperature increases in the question. This implies that volume also increases. So the option C is the right choice for this question. Now question number 13 is like this. A Carnot's engine absorbs 8 into 10 power 6 calories of heat from the reservoir at 607 degrees Celsius and rejects it to sink at 57 degrees Celsius. The work done by the engine is. So here this is the temperature of the source. I take it as T1 as per standard symbol. But 607 Kelvin or degree Celsius is equal to how much degrees Celsius? Add 27, how much Kelvin? So 607 plus 273. So when you add up, you get 880 Kelvin. Whereas the temperature of the sink, standard symbol is T2. It is 57 plus 273. It becomes 330 Kelvin. Now, efficiency we can find out. Efficiency of the Carnot's engine is 1 minus T2 by T1 equal to 1 minus 330. So remember, numerator when you write T2 by T1, it should be smaller number. You may forget the formula, but you can write properly. 880. Okay, so this is 1 minus 3 by 8 equal to take common denominator 8, it is 5 minus 8 minus 3 is 5. So efficiency eta is 5 by 8. Now we have alternate definition for efficiency. Efficiency is what? The work done to the ratio of work done to the heat supplied. That is W divided by heat supplied to the Carnot's engine Q1 from the source. Okay, heat absorbed, we can say. So therefore, this implies work done equal to efficiency into heat absorbed. Now substitute W value required. So eta value 5 by 8 we got. If you want in percent, if the question only efficiency calculation, you may require the answer in percentage. So multiply 100%. So 500 by 8. Okay, so that is the percentage value. Now here Q1 is given 8 into 10 power 6 calories. Okay, so that is 8 it cancels. So 5 into 10 power 6 calorie. So this is the amount of work done in this case. So 5 into 10 power 6 calorie means, say, option A and D. Numbers are same, but first option is joules. By chance you don't see your calorie in the given question, go for the option A, which is wrong. So the option here is D is the right choice. Alternatively, you can do here another way. Q2 by Q1, heat rejected to the sink upon heat absorbed from the source equal to T2 by T1. This is the another way you can go without finding efficiency. So we'll get the Q2 value. I said T2 by T1 already we calculated. T2 by T1 is 3 by 8. I write directly here. Okay, 330 by 8, 8 is 3 by 8 into Q1 is 8 into 10 power 6. Then 8 cancel. This is 3 into 10 power 6 calories. Okay. So then last what we need is work done. Work done by the Carnot's engine is heat supplied minus heat rejected. That is the work done. So that is equal to 8 minus 5, 8 minus 3. It is 5 into 10 power 6 calories. So this way also you can get without calculating the efficiency. So efficiency finding is important. Then I go to the next question. Okay, number 14. The RMS speed of molecules of an ideal gas at 27 degrees Celsius is 500 meter per second. What is the RMS speed of the molecule at 327 degrees Celsius? We know that RMS speed of gas molecules, we derived the pressure equation, and RMS speed is equal to 3 RT by M. This is the formula for RMS speed. At least you remember RMS speed is directly proportional to square root of the absolute temperature. It's enough to solve this problem. So which implies VRMS is proportional to root T. Now we want the RMS speed in the second case at a temperature 327. So I write VRMS dash upon VRMS equal to root of T dash by T. T dash, don't substitute 327 as it is. 327 is how much Kelvin? This is the T dash value. T dash is 327 plus 273 divided by 27 is there first case plus 273. When you add up, this comes to 600. Root of numerator is 600, denominator is 300. That is nothing but root 2. Okay. So therefore, new value of RMS speed, VRMS dash equal to root 2 times VRMS. Now the value of VRMS is initial case, first case at first temperature 27 degrees Celsius, it is 500. When you multiply 500 with 1.4, you get approximately 700. Little more than 700, say, because 1.4 into 500 is 700, is more than this. So 705 meter per second. The option is option B is correct answer for the question 14. Okay, I can go to the next question. This is a very important idea. See, VRMS, how it depends on M, inversely on M. If two different gases are given, different gas means different molecular mass, then inversely on mass square root is there. That part you have to take into this one. Here only temperature effect. Okay, then question number 15. At what temperature the RMS velocity of hydrogen molecule will be equal to that of an oxygen molecule at 127 degrees Celsius? So oxygen molecule RMS velocity is equal to at some temperature, say T, RMS velocity of hydrogen. So that is the question. The question is one sentence, but the logic you see, RMS velocities are same. So VRMS equal to V dash RMS. Two gas molecules have same RMS velocity. Now for first gas, if I write temperature T for hydrogen, so I write the formula. VRMS is given by 3 RT upon M. Okay, 3 RT by M. It is equal to root of 3 R same T dash. T dash temperature of oxygen gas is given 127 degrees Celsius. And what about M? M also different here. M also different. So 3R, 3R. Whenever square root is there, square both the sides. Therefore, we can compare easily. T by M equal to T dash by M dash, which implies T is required for us actually. So T dash into M by M dash. Okay. We can use the T1, T2 also, M1, M2 also. Okay. T equal to, substitute the values, T dash. So temperature of oxygen molecule 127, again conversion into Kelvin, add 273, it is 400 Kelvin. So substituting here 400 Kelvin into mass, M means mass of hydrogen. We can take 2, molecular mass 2, and oxygen molecular mass is 32. O2 it is 32. So it is M is 2 divided by M dash is 32. Okay. So this 1s are, this 16s are. Then we get here 400 by 16 is 25. And the temperature in Kelvin we get actually temperature in Kelvin. Now to get this temperature in Kelvin to degrees Celsius. So T equal to 25 minus 273. To convert it to degrees Celsius, subtract 273. So minus 248 degrees Celsius. Obviously 25 is there in the answer option A, but it is degrees Celsius. It cannot be the answer. Option D is the right choice. Okay. Then question number 16. A volume versus temperature graphs for a given mass of ideal gas are shown in the figure given below at two different values of pressure. What can be inferred about the relation between P1 and P2? So two gases are here in this. Okay, so gases at two pressures. So for this problem, what I do is here, I draw one either horizontal line or vertical line. So we can understand very easily. So if I draw a line, let's say at 20, like this. Okay. So at certain pressure value, volume is say 20, and P1 is the pressure at 20, and corresponding temperatures I get here. So now it is ideal gas. So therefore, what you can say in case of ideal gas, volume I fixed, same for both the curves, volume value. So therefore, when volume is same, pressure is directly proportional to temperature. Pressure is directly proportional to temperature. So drawing horizontal line at 20, that is say volume is 20 for both the curves. So we can see here volume fixed. Volume is fixed. Okay, 20 I fixed. Then ideal gas, when volume is fixed, so pressure must directly proportional to temperature. So here pressure P1 has a greater value of temperature compared to the pressure P2. Pressure P2 temperature is say 150 approximately here, whereas P1 it is 450. Therefore, the pressure P1 must be greater than P2. Pressure P1 must be greater than P2. Pressure P1 proportional to temperature T1, whereas P2 proportional to T2. So therefore, T2 is greater temperature, say at higher temperature 450 degrees Celsius, corresponding to P1. So therefore, P1 is greater than P2. P1 greater than P2 because the temperature T2 is here at say 450 Kelvin, whereas P1 is say 150 Kelvin. So more the temperature which is corresponding to pressure P1. More temperature, more pressure. Okay, so more pressure is for P1. Okay, therefore the option A is correct. We can understand by drawing vertical line also. Here we fix the volume. We can write the equation in two situations and divide and also get. So if I write the equation P1 into temperature, so P1 into volume, say 20, okay, equal to R into T. T is say 450, okay. Then next P2 into 20 only, volume is same, 20 only, whereas the R value into temperature is say 150. Okay, so then clearly R and R same 20, same. Therefore, P1 is 450, proportional 450. Therefore, it is greater. Then I go to the next question. 17. A cylinder of volume 2 into ratio -3 meter cube contains 0.1 mole of hydrogen gas, 0.2 mole of helium gas. The temperature of the mixture is 27 degrees Celsius. You can write it as 300 Kelvin. Now the pressure due to mixture of two gases. So according to Dalton's partial pressure law, total pressure P equal to pressure contributed by individual gases here. Two gases. It's a mixture of two gases. So P equal to the pressure P equal to PV equal to mu RT. So we want the pressure due to individual. So P equal to mu RT upon V it is. Okay, so the volume V same for both the gases because both the gases are in the same container. So it is mu1 first gas, mu1 R is same for both the gases, temperature also same, volume also same. So mu2 RT upon V. Okay, then substituting the values, it is bracket mu1 plus mu2. So mu1 first volume, that this one is 0.1 mole plus second mole is 0.2 mole of helium, 0.2 mole of helium. Then mu1 plus mu2 outside, whereas RT by V, simplifying, R is 8.31 into temperature 300, it is given 27, right in Kelvin, 300 upon volume 2 into 10 power minus 3. Now it is 0.3, okay, 0.3 into 8.31 into 300 divided by 2, 300 divided by 2 into 10 power 3 I write, numerator, 10 power 3. Simplification is very simple. 0.3 into 300 is 30 into 3, 90, 90 into 8, 90 into 8 around 700 plus 750 approximately. 750 by 2 is 375. 375 into 10 power 3, or we can say 3.75 into 10 power 5. So this is the final pressure or pressure due to both the gases together. So option C is the correct. So individual pressures we calculate, total pressure we'll get. So individual pressures contribute to the total pressure. We can add the two pressures according to Dalton's partial pressure law. Then question number 18 is like this. A mixture of two gases contains 2 moles of nitrogen and 4 moles of neon at temperature T. Assuming that there are no vibrational modes. Vibrational modes are not there. The internal energy of the system is. Means vibrational modes are not there means the energy is due to only rotational and translational modes of vibration. So firstly, how to calculate the internal energy? So internal energy U equal to. So there are mu moles of a gas, mu moles of a gas. In 1 mole, there are Avogadro number of molecules. So mu moles of a gas, how many molecules are there? Mu into Na. Now, what is the energy of each molecule? That is according to law of equipartition of energy, degrees of freedom multiplied by half kBT. So this is the law of equipartition of energy. Energy of any molecule or any system is equally distributed among various degrees of freedom. The energy associated with each degree of freedom is half kBT into number of degrees of freedom, that is for the gas. So that will be the energy of molecule. So bracket term represents the energy of one molecule. Mu into Na number of molecules are present. So therefore, this also note that Na into Kb. Na into Kb is how much? Na into Kb equal to, it is R. Na into Kb, where Na is Avogadro number, Kb is the Boltzmann constant. Okay, so the product becomes R. Now, say total internal energy, there are two gases. So internal energy is sum of the two internal energies. So U equal to U1 plus U2. Okay, U equal to U1 plus U2. Okay, then we can write this formula, mu into Na into Kb is R. So mu into F into R into T. Okay, divided by 2. This is the internal energy of any one kind of gas. So there are two gases, mixture of two gases. So U equal to, here number of moles, mu different, F different, RT by 2 is same. So it is mu1 F1 by 2 plus mu2 F2 by 2 into R. Okay, so RT. You can take a T 2 also out. Okay, so RT by 2 common. So then it becomes just substitution mu1 number of moles in first gas 2. Now degrees of freedom of that gas, nitrogen is diatomic gas has 5 degrees of freedom. Okay, so 3 degrees of translational degrees, okay, and 2 rotational degrees, so 5 plus mu2 for the second gas, 4 moles are there. It is a neon gas. Neon is monoatomic. It is 3 degrees, only translational degrees of freedom are present. Then into RT by 2. Okay, so RT by 2. Now simplifying this, we'll get the answer. So it is 2 into 5, 10 plus 12, 22. 22 inside the bracket by 2 is 11 RT. So the answer is option D, 11 RT. That is the total internal energy of the system. Then I move to the next question. Question number 19. The average translational kinetic energy of nitrogen in 2 moles, nitrogen molecules it is, in 2 moles of gas kept at certain temperature is 0.56 eV. Understand, average translational kinetic energy of molecule, not the entire substance. This is for one molecule. Now, average translation kinetic energy of helium atoms in 4 moles of gas. So in each case, each molecule energy we have to get. So translational kinetic energy, okay, so degrees of freedom, how much? It is 3 for nitrogen also, 3 for helium also. So degrees of freedom same. It is dealing with only atom here. Whatever the number of atoms present in the gas, it doesn't matter. The average energy, translational kinetic energy of every molecule you are considering. So the number of molecules is immaterial in this. Okay, even 2 moles, 4 moles also, that is not important. So here 0.56, the degrees of freedom, translational degrees, 3 here, same for both. So F is translational degrees of freedom, F is same for both. So therefore the answer is, okay, same for both. F, that is translational degrees I am telling. F translational degrees of freedom, same for both the gases. Hence the answer will be same, that is 0.56 eV. Then the next question, number 20. A vessel contains a mixture of 1 mole of oxygen and 2 moles of hydrogen at 330 Kelvin. The ratio of average rotational kinetic energy of the oxygen molecule to that for hydrogen molecule will be. So we have to get here the ratio of the rotational kinetic energy. See again, oxygen diatomic, or it is a rotational we are dealing here. Rotational degrees of freedom 2 for oxygen diatomic, and for hydrogen also it is diatomic. Rotational degrees of freedom 2, translational 3, but it is not required, only rotational. So therefore both will have the same rotational kinetic energy. Average rotational kinetic energy same for oxygen as well as hydrogen. Hence the ratio is 1:1. The next question 21. When 2 gases considered under identical conditions, temperature, pressure, volume, the ratio of the mean free path of the molecules of 2 gases having molecular diameters 1 angstrom and 2 angstrom. So mean free path, average distance between successive collisions. Mean free path L dash inversely proportional to square of the distance. Okay, so actual formula L dash equal to 1 by root 2 pi n d square. This is the formula where n is the number density of molecules, number of molecules per unit volume, and d is the diameter of the molecule. See here the ratio of the diameter, you see ratio of the diameter is 1:2. The easy way you can get, we want d square, so d square is 1:4, whereas L dash, that is Mean free path inversely proportional to square of the diameter. So L dash is proportional to inverse ratio, that is 4:1. So the answer is option D. If you want exact calculation, so L by L by, okay, so L bar divided by L bar dash I write, okay, or L dash bar equal to inversely on diameter. So D will come here, D dash here, square. So D dash, it is 4 angstrom, 2 squared actually. So 4 by 1 it is. Okay, 2 by 1 square is 4 by 1. So the option D is correct. Then 22nd question. If 70 calorie of heat energy is required to raise the temperature of 2 mole of ideal gas at constant pressure from 30 to 35 degrees Celsius, then the increase in internal energy of the gas is, R value is given. Increase in internal energy. So some heat is supplied to the gas, change in temperature takes place, the 2 moles of gas is present, then internal energy, how much it changes. So previous problem we found internal energy of the system. Here change in internal energy, it is based on the first law of thermodynamics. So firstly, let us find out what is the work done. Work done equal to PdV. Okay, PV equal to mu RT. Okay, or nRT also you can write. So PdV equal to, you can write mu RT. Why? Because volume mu R dt. Okay, mu R dt. Mu R into dt, change in temperature. Because here change in temperature is given, not volume. So therefore mu is given, the number of moles in the substance 2 moles. The R value, they gave R value 2 calorie. By mistake don't substitute 8.31. In terms of calorie, it is 2 calorie per mole per Kelvin into change in temperature. Okay, from 30 to 35, it is 5. You may ask whether it is okay if you say take in degree Celsius. It is the difference in degree Celsius and difference in Kelvin scale will be the same. 30 to 35 difference is 5. In Kelvin also it will be 303 and 308. Difference comes 5 only. So 4 into 5, 20 calorie. So 20 calories is the work done. So then we have now, okay, I can write dW also. Now using the first law of thermodynamics, heat supplied, it is at constant pressure. Say I write QP is equal to change in internal energy or increase in internal energy. I can write say du plus dW. Okay, so this I take dW work done symbolically, no problem. So this implies we ask to find out du, change in internal energy. So Q, heat supplied minus dW. Okay, heat supplied also you can take delta Q or dQ. So that is equal to difference, just difference. So dQ is given 70 minus dW work done, we calculated it is 20. So it is, the answer is 50 calorie. 50 calories, option C. So this is the amount of change in or increase in internal energy. The last question, air contained in non-conducting cylinder is allowed to expand adiabatically so that its volume increases by 10%. So when volume increases by 10%, V becomes how much? 110 V, 110% V, that is 1.1 V. So what happens to pressure? Pressure, what happens? That's all. So it is adiabatically. So again, PV power gamma equal to P dash into 1.1 power 1.1 V power gamma. So this implies P dash equal to, see, V power gamma cancels. Okay, so it is P into 1 by 1.1 power gamma. Okay, gamma for this gas, it is air here. For air, gamma value we can take approximately 1.4 because air contains most of the diatomic molecules. So gamma value, ratio of specific heats can be taken as 1.4. So this is P into, say, 1.1, approximately ratio of 1.1. 1 by 1.1 is nearly 0.9. To go with calculator, it become 0.91. but approximately 0.9. Okay, so then 0.9 power gamma. Gamma is 1.4. Now this number is there. It is less than anyway, less than 0.9. As you increase the power, when a number is less than 1, it becomes smaller and smaller. So 0.9 power 1.4 is less than 0.9, maybe 0.87 or 0.86. So 0.87. So that means it is decreased by 13%. So the option D is the right answer. Here the shortcut we can apply. See, when pressure volume increases, pressure must decrease. Pressure must decrease when volume increases. In case of adiabatic process also, isothermal process also. Okay, so therefore the options decrease, only one option is there, hence the option D must be the right answer. Now see, so far I have discussed many of the questions related to both the chapters. So difficult questions were there, some were long questions, easy questions, short questions. So try to solve the questions which are easy you find in the first round. Attempt some 30-35 questions comfortably, then go for long, lengthy questions. Whenever you solve lengthy questions, read carefully, because every data is important there, and it will take time to read. And if you go for next question, it's waste in reading the question. So without wasting much of the time in the exam, keep on solving. And whenever you get some doubts on the answers among options, just put a question mark. It may be the possible answer in the guesswork. Okay, so see you. All the best. God bless you. That's the end of this session.